Figure 8 shows a sketch of the curve C with equation y equals x to the x, x greater than 0. So it's not an exponential because that's when you have, say, 2 to the x or 3 to the x. Actually, the base is also changing. And we get a turning point still. Here it is, when we're being asked in part A to find it. But we're asked to firstly take logarithms. That means actually take ln of both sides, or ln if you prefer. So ln y will be ln x to the x. Then I can bring that x down so it becomes x ln x. And what we can now do is differentiate both sides with respect to x. On the left, well, it's implicit differentiation. So on the left, I'm going to differentiate ln y with respect to x. We get 1 over y multiplied by the derivative of y, which is dy by dx. That's how implicit differentiation works. Because if you had, say, ln of 2x squared plus 3, and you differentiated it, then you'd get 1 over 2x squared plus 3, and then you would times by the derivative of the inside, which is 4x in this case. I'm actually doing the same thing. I'm doing 1 over y and times it by the derivative of y. Then for x ln x, I'm going to use the product rule. So I call this u, and this v, for example. So it's u dash v, which is just ln x, plus u v dash, so x times 1 over x, which gives us ln x plus 1. And we're one step away from finding dy by dx. It's just going to be ln x plus 1 times y, which remember is x to the x. It's going to be this. This is known as logarithmic differentiation. It's pretty awkward if you've never seen it before. Your alternative that was allowed in this question is to do the following. So we've got y equals x to the x. You can differentiate it using a little trick. We want to write it as e to the power of something. In fact, it would be e to the power of ln x to the x because they're opposites. And then we can write it as e to the x ln x. So now when I differentiate this, I would get e to the x ln x as normal, differentiating the outside, that's just e to the something, times by the derivative of the inside, and then I'm going to get my ln x plus 1 again. And e to the x ln x, remember, is x to the x, so we get exactly the same answer. So normally when I teach how to differentiate 2 to the x and so on, I do this method here. I don't start bringing in logarithmic differentiation. But hey, look, you've seen it today. You know, it's something to be aware of and it can be really effective. We're not quite finished then. So we've got a result, but we're actually asked to find the turning point. So that's when dy by dx, of course, is 0. Now x to the x, we can see for these values is never 0. So we can just ignore that. It's going to be when ln x is equal to minus 1, or ln x plus 1 is 0. And that means that x is going to be e to the minus 1. And we're only asked, I think, for the x-coordinate, so that is it, e to the minus 1 or 1 over e. In part B, we're told that the point P alpha 2 lies on C. So that is a value of alpha, or value of x, I should say, that's going to give me 2. I'm asked to show that alpha is between 1.5 and 1.6. I'm going to do this up here. I'm trying to solve 2, so this is part B. 2 equals alpha to the power of alpha. Do you know what? I'm going to leave it as x for the moment. 2 equals x to the power of x. So that means I want to solve x to the power of x minus 2 equals 0. And I'm going to be using the sign change rule here. I always like to write a function down that's equal to 0. So let f of x equal x to the x minus 2. And we want to solve f of x equals 0. So what we can do is we can put in 1.5 and show that it's either positive or negative, and then it swaps around for the other one. I would strongly advise doing it like this rather than trying to show that you could put in 1.5 into x to the x and show that it's less than 2, and then 1.6 means that it's bigger. But I'd say this is a slightly better way of doing it. So 1.5 to the power 1.5 minus 2. This one not minus 2 like that though. Minus 2. I'm expecting this one to be negative. So minus 0.162. Now still with the 1.6. 0.121. So there's a sign change. F of x continuous over the interval. I always think this is a good one to write down because you can get sign changes without a root. For example, 1 over x jumps from negative to positive without actually going through the axes. But here what we're saying is, look, it's this function. I don't know exactly what it looks like. Well, it's going to look like x. It's going to look like this function we've drawn, but minusing 2. So we're saying it's negative, then it becomes positive. Because we know that it is continuous, then it's going to be somewhere in between that it goes through that through the x-axis. That's our root. And therefore, we can say that alpha is between those values. That's it. A possible iteration formula that could be used in an attempt to find alpha is given by this: xn plus 1 equals 2xn to the power of 1 minus xn. Let me just explain where that came from. We've got 2 equals x to the x. If I divide through by x to the x, I'd actually get 2x to the minus x is 1. And I could times through by x. The left-hand side, I would then add 1 to the power. So I get 2x to the 1 minus x. On the right-hand side, I just get x. So it's equivalent to me solving the original equation. And I can turn this into an iterative process using fixed point iteration. We plot y equals x, then we plot our curve. I'm not really sure what it looks like. We have a starting value, and then you basically keep putting it in, and it will, in, well, some circumstances, including this one, converge towards the root. We're going to see there's a few complications in our case though. So we don't need to know about that in this question, but sometimes you are tested on it, so I wanted to talk about it. We actually just need to substitute x, the first value is 1.5, put it into here and just keep getting values out. So 1.5 equals gets it into the answer button, and I've got 2 answer the power of 1 minus answer. This is exactly the same formula. So this will give me x2. Could write it down. It's only asked me for x4. That would be x3. This one would be x4. So 1.6731. Which is going to round to 1.673 to 3 significant figures. And finally, we're asked to describe the long-term behavior of xn. So just got to keep pressing equals and see what happens. And actually, it doesn't look like it's converging, in fact. It's jumping between 1 and 2. So we're not managing to find the root using this method. It's actually failed. So we just need to write something along those lines. I wrote oscillates between 1 and 2. There's numerous things that the mark scheme allowed. So I'm just going to show you. Okay, so if you say the word oscillate, periodic, non-convergent, divergent, fluctuates, goes up and down, 1, 2, 1, 2, 1, 2, then you're okay. Now we need to say something like it oscillates between 1 and 2, or it's periodic. There's a few other things allowed. So basically get the 1, 2 in there, I would say, and then the word oscillate or something like that, and you'll be okay. Last little comment, thanks for sticking around for it. I've decided to plot the graph of y equals x and y equals 2x to the 1 minus x and show you how the fixed point rotation is working. So we can see the roots here between 1.5 and 1.6. We know it's there, but when we put in 1.5, although it feels like it's going to spiral in towards it, it actually ends up just spiraling out like this. You can see once on this path, it's just going to keep going. Gets closer and closer to that 1 and to the 2 until essentially it hits them, and that's when it's just going to go around this loop forever. So that is why it oscillates in such a way. So let's just kind of replay that. So I'm putting in 1.5 equals, I'm going back to my formula. So that's when it goes up the first time to 1.6, but when it comes back round, it gets slightly less than the 1.5, then it gets slightly more, then slightly less again than the 1.5, and you can see it's spiraling out. That process that I was just talking about. Yeah, we're on the outer bit now. We're going near to 1, near to 2. If you just keep going, then this is just a calculator can't deal with it anymore. It's not quite 1, it's not quite 2. It's just probably getting closer and closer, but it's going to converge towards those two. So quite an interesting one, really. Even though we start really close to the roots, the fixed point iteration fails. The question doesn't go into that level of detail. It just asks for the long-term behavior, but that is in depth what is going on. Anyway, well, this is an interesting question. Logarithmic differentiation to start with, then just throwing in the sign change rule, then fixed point iteration and long-term behavior of it oscillating instead of converging without going into all the depth that I have. It's a nice question. Well done on your efforts on it.